Look at any picture of the sun you can call to mind. Choose the most detailed one, the kind that fills a screen with churning orange. Dark freckles of sunspots crawling across the middle, ribbons of fire arching off the rim. Now notice something about that image, and about every other image of the sun you have ever seen. They all show you the same part of the star, the middle, the blazing belt around its equator, photographed straight on, as though the sun had spent the whole of human history turning only one region of itself toward our cameras and quietly refusing to show the rest. For thousands of years, from the first crude telescope pointed at a safely projected reflection to the most sophisticated observatory ever flown, we photographed our nearest star the way you might photograph a stranger who will not lift their head. Always the front, always the broad, bright face. Never the top, and never the bottom. This is true of the famous space telescopes that watch the sun without blinking, the ones that give us those gorgeous high-definition movies of flares erupting in real time. It is true of the probes that hover at a fixed point between us and the sun, keeping a permanent, unobstructed view. It is even true of the rare and treasured photographs taken during a total eclipse, when the moon blocks the disk and the faint outer crown leaps into view. Every one of those images, without exception, was captured from roughly the same level, looking at roughly the same belt around the star's waist, and until very recently, almost no one outside a small circle of solar physicists understood that the most photographed object in our entire sky carried a permanent blind spot, stitched into every picture we had ever taken of it. The two caps at the sun's poles, the regions at its very top and very bottom, were never properly seen. Not faint, not half-glimpsed through haze, simply unseen, in any clear and honest sense of the word. Then, in 2025, a spacecraft named Solar Orbiter finally lifted itself high enough above the level of the planets to look down at one of those caps for the first time. And what it sent home did something quietly disturbing. It did not reveal a monster lurking at the pole. It revealed a region of our own star behaving in a way that nobody could fully explain, sitting in the exact place we had always been forced to ignore. The premise of this story is a strange one, that what lies above and below the sun is more frightening than the empty dark between the stars. On the surface, that sounds like overstatement. The void, after all, is the great nothing, the cold blackness that seems to swallow meaning itself, the classic stage for every fear we have ever projected onto the sky. But there is a careful and entirely honest version of that claim. And it starts from a single fact that ought to unsettle anyone who hears it for the first time. We managed to map the faint glow at the very edge of the observable universe before we managed to take one clear photograph of the top of the sun. We charted the afterglow of creation itself before we charted the lid of our own lantern. That blind spot was not carelessness. It was not a failure of nerve or budget alone. It was geometry. And a blind spot built from geometry is far harder to dismiss than any tale of haunted distances, because it does not depend on our tools being weak. It depends on where we are allowed to stand. A gap in our cameras can be fixed with a better lens or a longer exposure. A gap in our vantage point cannot be fixed by any amount of cleverness applied from the wrong position. For the whole arc of astronomy, we were standing in the one place that guaranteed we would miss the two most decisive regions of the star our lives depend on. And we did not even feel the limit, because we had never known anything else. We assumed the face was the whole. We assumed the bright middle told the full story. That assumption felt complete. The way a portrait feels complete until someone gently points out that it was only ever a profile. That the back of the head was never in the frame, and you simply never thought to ask what it looked like. Among solar physicists, this gap had a quiet, almost resigned name. The polar magnetic field was the great unmeasured quantity, the one number at the heart of the sun that every model needed and no instrument could pin down with confidence. From the disk, looking at the cap edge on through the thick, foreshortened slice of the sun's atmosphere, the delicate measurements of magnetism smeared together and partly cancelled out, so that even the rough estimates carried wide uncertainty. Models of how the sun behaves over decades had to be fed a guess for that polar number, and the guess shaped everything that came out the other end. Generations of researchers simply learned to work around the hole, the way you might learn to live in a house with one room you can never enter, building your whole life around a locked door and slowly forgetting it is even strange. The poles were always in the data as an absence, a region where the error bars opened wide and the honest answer was a shrug. And the strangest part is how invisible that absence was to everyone else. The public saw flawless, high-definition images of the sun streaming down year after year, each one sharper than the last, and reasonably assumed we had the star thoroughly mapped, the way we have the Earth mapped down to individual streets. No one mentioned that the top and the bottom were missing, because in the gorgeous edge-on view, there was no obvious empty space to point at. The cap was simply at the rim, present in every frame and unreadable in every frame, hiding in the brightness rather than in any darkness. So before we lower our gaze into that cap of tangled plasma and ask what it actually means, we have to understand the trap itself. We have to understand why. For all our brilliance, for all the centuries of careful and obsessive watching, we kept missing the top and the bottom of the closest star to Earth. Because the answer is not that the poles were hiding from us, or that they were too dim, or too small, or too far. The poles blaze just as fiercely as the rest of the sun. The answer is that we were never positioned to look at them. And the reason we were never positioned to look says something profound about the shape of our entire neighborhood in space. Something most people have never once been asked to picture clearly in their minds. It is a fact about where we live that quietly determined what we could and could not know for the whole of recorded time. The cause of the blind spot is the shape of the solar system itself, and it is not the shape most people imagine. We tend to picture the planets scattered around the sun in every direction, like a swarm of bees hovering around a flower, drifting freely above and below and all around it. But that is not how our system is built at all. Earth, and every other major planet, travels around the sun on very nearly the same flat level, like marbles rolling around the inside of a shallow dish. Astronomers call that level the ecliptic plane, and it sits almost exactly in line with the sun's own equator, its waistline. So picture the entire solar system as a vast flat record turning on a turntable, with the sun as the glowing label at the center, and the planets as grooves running around it at different distances. Now ask where every telescope, every observatory, every sun-watching spacecraft in history has actually sat while it watched. Every single one of them sat on the record, or very close to it. They had no real choice in the matter. We launch our machines from a planet that lives on the disk, and that planet is moving sideways around the sun at tremendous speed, tens of kilometers every second. Anything we launch inherits that enormous sideways motion the moment it leaves the ground, like a passenger thrown forward when a train stops. Except the throw never ends. So our machines naturally settle into orbits that lie on the same flat disk, carrying the momentum of their home world with them. And from anywhere on that flat turning record, the sun is seen edge-on, level with its middle. The poles, the top and the bottom, are always tilted away at the far rim of the view, squashed and smeared by the steep grazing angle, like trying to read words printed on the top edge of a coin while holding the coin level with your eye. You can sense that something is written there. You can squint and perhaps guess at a letter or two from the way the light catches it, but you cannot read it, and you certainly cannot photograph it cleanly, no matter how fine your instrument. That was the cage we lived in for the entire history of watching the sun. Not a cage of dimness or distance, because the poles are right there, as bright and close as everything else. A cage of position, of geometry, of the simple fact that we were standing in the wrong part of the room. To see the top of the sun properly, you would have to climb up off the flat record entirely, rise high above the level of every planet, and look down at the central label from a height that no natural orbit would ever give you for free. And here the trap tightens into something that feels almost deliberate, though it is only physics doing what physics does. Climbing up off that plane is one of the most fuel-hungry maneuvers a spacecraft can attempt, far more demanding than simply travelling to a distant planet. Everything about the solar system wants to keep your machine on the disk. The vast sideways speed your craft inherited from its home planet is constantly carrying it along the flat path. And to lift its orbit out of the plane, you must fight that inherited motion head on, burning a staggering amount of fuel to bend your trajectory upward against it. For decades, the cost of that climb was simply beyond any mission's reach. So the poles stayed exactly where they had always been, at the ragged edge of every image, present but unreadable, a region we knew was there and had quietly trained ourselves to stop expecting to ever see clearly. There was, however, one way through the wall that did not depend on carrying impossible amounts of fuel. One loophole written into the laws of motion themselves. Instead of fighting the inherited sideways momentum with engines alone, a spacecraft could borrow a shove from a planet. By flying close to a world and threading past it at exactly the right angle and speed, a probe can trade momentum with that planet's gravity, using the encounter as a kind of slingshot to bend and reshape its own path through space. The planet barely notices, but the tiny craft can come away with its orbit dramatically altered. Do this cleverly, again and again, returning for pass after pass, and you can slowly tilt your orbit higher and higher up out of the flat record without ever having to carry the enormous fuel such a climb would otherwise demand. Each encounter lifts you a little further above the plane. That is the loophole that finally cracked the cage. And it means that the most important journey in this entire story, the journey that at last let human eyes look down at the top of the sun, did not begin at the sun at all. It began with a series of careful, patient passes by a hot, cloud-wrapped world that almost nobody pictures when they picture the sun. It is worth dwelling on just how patient and counterintuitive that solution is, because it runs against every instinct we have about how to reach a destination. To look at the top of the sun, the spacecraft does not aim for the sun's pole and fire its engines toward it. Instead, it spends years flying inward toward Venus, again and again, never touching the planet, only skimming past it at carefully chosen distances and angles. Venus is the right partner for this, because it orbits closer to the Sun than Earth does and carries a great deal of orbital momentum, enough to lend a meaningful push on each encounter. and because its position can be timed to meet the spacecraft pass after pass. Each flyby bends the craft's path a little, tilting the orbit by a few more degrees out of the flat plane and reshaping its loop around the Sun. None of it is sudden. There is no single dramatic moment of climbing. There is only the slow accumulation of small gravitational nudges, spread across years, each one lifting the spacecraft's eventual viewpoint a fraction higher above the equator of the star. It is less like launching a rocket straight up, and more like a long, deliberate spiral staircase, where Venus is the pivot the whole climb turns around. And the deeper irony is that to rise above the Sun, the craft must repeatedly fall toward the inner solar system, trading closeness to one world for height above another. The path to the top of our star runs not outward into the dark, but inward, toward the hot, bright, cloud-smothered planet most people never associate with the Sun's secrets at all. It began, of all places, at Venus. You might fairly ask why anyone would spend years of planning and a fortune in engineering simply to photograph the lid of a star we have stared at for as long as we have had eyes. We already knew the Sun was an enormous ball of hot gas. We already knew it had storms, spots, and eruptions. Why should the top and bottom matter so much that they justify bending a spacecraft's entire orbit up out of the plane of the planets, one expensive Venus pass at a time? This is the point where the comfortable picture of the Sun begins to crack, because the poles are not a missing scrap of scenery, not a pleasant extra view that merely completes the collection for the sake of tidiness. There is a strong scientific case that the poles are the part of the Sun that quietly governs the rest of it. Almost everything most of us picture when we imagine solar drama, the dark sunspots, the sudden brilliant flares, the great eruptions of glowing matter flung off into space, happens in the busy middle latitudes, the very regions we could always see. That is the part of the Sun that performs for the audience, the part that fills the documentaries and the news alerts. But the poles, the calm-looking caps at the top and bottom, are where solar physicists believe the deeper machinery sits, the part that decides what the performance will be before a single spot appears. The magnetic field gathered at the poles appears to behave like a stored charge, a kind of reservoir that quietly sets the terms for what comes next. The strength of that polar field, measured at the right moment in the Sun's long rhythm, seems to forecast how fierce or how mild the following years of solar behavior will be, in much the way the charge held in a battery before it discharges tells you something about the surge of power about to be released. A strong polar field tends to be followed, several years later, by a more active and more violent stretch of the Sun's life, a busier cycle full of spots and storms. A weaker polar field tends to be followed by a quieter, gentler stretch. So the region we could measure least is, plausibly, the region that sets the tone for everything that follows, the place where the next chapter is drafted before any of us can read it. And there is a second reason the poles matter, every bit as strange as the first. They are the birthplace of the fastest stream of material in the entire solar system. The Sun is forever bleeding a wind of charged gas out into space in every direction. But this wind is not uniform. Near the poles, the Sun's magnetic field lines tend to open up and reach straight out into space rather than looping back down to the surface. And along those open lines, the gas escapes freely and races outward, forming a fast wind that pours from the polar regions far quicker than the slower, more congested wind that struggles out from nearer the equator. The poles, in other words, are where the Sun most efficiently throws its breath into the rest of the system. Put those two facts side by side, and a deeply uncomfortable realization takes shape. The part of our star we understood the least is also the part that seeds its cycles of activity and launches its fastest wind into the space all the planets share. We had, in effect, been studying a great and powerful engine by pressing an ear to the wall around it. We had learned the rhythm of its pistons, the timing of its surges, the rising hum that signals something building. We had grown genuinely skilled at predicting, from the muffled noise alone, roughly when the next burst of power was coming. But we had never once seen the part of the machine that actually decides when those pistons fire. The control region tucked into the two corners of the housing, where we could never get a clear line of sight. For most of history, that did not even feel like a failure, because we had no idea the control region was where it was. We thought the noise was the machine. We thought the visible storms in the middle were the source of the whole story, rather than the downstream consequence of decisions being quietly made out of our sight. Up at the caps. It is the difference between watching the actors on a brightly lit stage and never once glancing at the wings, where the cues are called and the scenery is changed and the real shape of the play is decided. To understand why the wind escapes so freely from the poles, it helps to picture the two kinds of magnetic terrain on the Sun. In most places, especially around the busy middle latitudes, the field lines arch up out of the surface and loop straight back down again, forming closed arcades that trap the hot gas beneath them like the bars of a cage, letting only the slower, more reluctant wind seep out around the edges. But near the poles, large regions open up instead. There the field lines stretch outward and do not return, reaching straight off into space like roads with no end. And along those open roads, the charged gas simply pours away unimpeded, accelerating outward into the fast wind. These open regions tend to appear darker and cooler in certain kinds of imaging, and they are known as coronal holes. The largest and most persistent of them sit at the poles, two great open doorways at the top and bottom of the star, through which the Sun most freely exhales into the rest of the system. So the poles are not merely where the wind happens to be fast, they are structurally the easiest place for the Sun to lose material at speed, the open gates in an otherwise caged surface. That is yet another reason the polar field matters so much. The arrangement of open and closed field lines up there governs how much of the Sun's breath escapes and how quickly, and that in turn feeds directly into the wind that fills the entire system. We had been trying to understand the Sun's exhalation, while unable to see the largest, most open doorways it breathes through. The moment you understand that the poles may be the controllers rather than the spectators, the whole familiar Sun rearranges itself in your mind. The bright, performing middle becomes the stage, and the unseen caps become the wings where the actual choices are made. And to understand how those choices get made, to understand what the polar machinery actually is and why it behaves the unsettling way it does, we have to stop listening through the wall altogether and look directly at the engine itself, at the churning, spinning, self-winding heart of the star. The first thing to abandon is the idea that the Sun has a surface in any ordinary sense. There is no crust, no shell, no solid ground anywhere on it that you could stand upon or drill into or even press your hand against. The Sun is a colossal sphere of plasma, gas heated so ferociously that its atoms have been shredded into a roiling swarm of charged particles. And that charged swarm is never still for a moment. Deep in the core, energy is released by the fusion of light elements, and it works its slow way outward over an immense span of time. And in the outer layers, that heat drives a constant, titanic boiling. Hot plasma rises in great columns toward the outer regions, spreads across the top, radiates its heat into space, cools, and sinks back down to be reheated, over and over, in a churning motion that never pauses. A little like the rolling surface of a pot of water just before it reaches a full boil, but on a scale that would swallow entire worlds without a ripple. If you could look closely at the visible layer of the sun, you would see it is not smooth at all, but covered in a restless, granular pattern. Countless cells of rising and falling gas, each one larger than a continent, constantly forming and dissolving as the heat churns beneath. Now comes the part that turns this churning into something far more interesting and far stranger than a merely hot fluid. That plasma is electrically charged, and whenever charged material moves, it generates magnetism. So the whole sun, churning in its restless depths and turning on its axis, becomes a vast, self-running magnetic machine, a process scientists call the solar dynamo. It builds its own sprawling magnetic field out of nothing but its own motion, endlessly, with no outside help and no off switch. And the field this machine produces is not gentle or simple, because the sun does not spin as a solid body like the Earth does, being made of fluid. Its equator rotates noticeably faster than its higher latitudes near the poles. The equatorial regions complete a turn in roughly 25 days, while the polar regions lag well behind, taking something closer to 35 days to come around. This is called differential rotation, and its consequences are enormous. Because the magnetic field is effectively frozen into the plasma and dragged along wherever the plasma goes, so the faster middle is constantly sweeping ahead of the slower top and bottom, lapping them turn after turn, and stretching the magnetic field between them as it goes. Imagine wrapping a single long rubber band around a spinning ball whose middle turns faster than its ends. With every rotation, the band is pulled, stretched, twisted, and wound a little tighter, growing more strained and more tangled, storing up tension with each pass. That, in rough but fair terms, is what the sun does to its own magnetic field over the slow years of a cycle. It begins each cycle in a relatively tidy arrangement, with a clear north and a clear south, a giant version of the simple bar magnet from a school science drawer, the kind whose invisible field you can trace with scattered iron filings looping neatly from one end around to the other. But the uneven spin keeps winding that tidy field tighter and tighter, season after season, year after year, until the neat arrangement can no longer contain the strain building inside it. The wound-up tension has to escape somewhere, and where it finally bursts up through the outer layers, it surfaces as intensely knotted regions of concentrated magnetism. These knots are slightly cooler than their surroundings, because the dense magnetic field chokes off the rising heat beneath them, and so they appear to us as the dark sunspots, the famous freckles, along with the flares and eruptions that tend to cluster around them like sparks thrown off a strained cable. So the calm, tidy sun of low activity and the spotted, stormy sun of high activity are not two different stars. And they are not two different moods. They are the same star, caught at two stages of one continuous process: the early, loose winding, and the late, strained tangle. The spots are simply the visible places where the overwound field has finally punched its way through to the surface. And because the winding never stops while the cycle runs, the strain only ever grows, accumulating relentlessly until the field reaches a breaking point it cannot pass without doing something drastic and total. There is a quietly remarkable detail in how those knots reach the surface, worth pausing on because it shows how alive the whole process is. When a bundle of magnetic field grows strong enough deep in the churning layers, it actually becomes buoyant. The intense field pushes some of the plasma aside, making that bundle lighter than its surroundings, and so it rises like a cork held underwater and released, floating up through the boiling gas until it breaks through the surface in a great loop, anchored at both ends, with a dark spot at each foot where the field plunges back down. That is why sunspots so often come in pairs, the two ends of a single buried loop that has surfaced. The strain wound into the field does not leak out evenly. It surfaces in these dramatic, structured eruptions, the wound-up tension finding the weakest points and bursting through in loops large enough to swallow the Earth many times over. And the most sobering thing about the whole self-winding machine is that it never rests and never requires winding by any outside hand. There is no spring being tightened by an unseen force, no fuel being added from outside. The sun's own rotation and its own churning heat are forever rebuilding the very field that strains and breaks and reverses. An engine that powers and winds and tears down and rebuilds itself in one continuous motion, and has done so without pause for billions of years. The cycle is not something that happens to the sun. It is something the sun is constantly doing to itself, by simply existing and turning. Roughly every 11 years, the wound-up machine reaches that limit and performs an act so extreme that if it happened to our own planet, it would feel like the sky itself had betrayed us. It does not simply release the built-up tension and relax. It throws its entire global magnetic field into reverse, tearing down the whole arrangement it has spent a decade laboriously building, and rebuilding it the opposite way around. And the place where that violent rebuilding is thought to play out most dramatically is, with a kind of cruel precision, exactly the place we could never watch. Picture a compass that has pointed faithfully north your entire life, suddenly deciding, with no warning and no apparent reason, that north now lies in the opposite direction. Picture every compass on Earth doing it at once. That is, in essence, what the sun does on a regular schedule to its own global magnetic field. The great field that had wrapped the star like a bar magnet weakens, falls into disorder, and then reassembles itself completely flipped, with what was the north magnetic pole becoming south, and what was south becoming north. This is not a doomsday rumour wearing the costume of science. It is one of the most firmly established rhythms in all of solar physics. Watched, recorded, and confirmed across many separate cycles by generations of careful researchers using a variety of methods. The reversal happens around the peak of solar activity, the stretch scientists call solar maximum, when the sun is at its most heavily spotted, its most restless, and its most prone to eruptions. The number of sunspots climbs to its height, the flares grow more frequent, and somewhere within that turbulence, the old magnetic order quietly comes apart, and the new, reversed order assembles itself in its place. And the poles are exactly where this flip is believed to express itself most starkly, because the poles are where the old field has to be dismantled down to nothing, and the new, reversed field has to be built up out of the wreckage. For decade upon decade, this was the deepest and most maddening frustration of the entire field of study. The reversal of the global field appears to begin and resolve at the poles. The polar field appears to plant the seed for the cycle that will follow, and the poles were the one stretch of the sun we could not photograph from a clear angle. We were trying to understand a magnetic heartbeat while watching everywhere except the chambers where the beat is actually generated. We could feel the pulse plainly enough, downstream, in the spots and the storms and the flickering of our technology, but the source of it stayed stubbornly behind the wall of geometry. Then, in March of 2025, Solar Orbiter at last tilted high enough above the plane to gaze down at the sun's south pole during exactly this turbulent, reversing stretch of the cycle. One of its instruments, designed to read the magnetic field directly, mapped the polarity across the cap rather than guessing at it from the side, painting a picture of which way the field pointed at each patch of the pole. And what it found was not a clean, single polarity. It was not a tidy southern cap calmly waiting its turn to become northern. It found disorder. Patches of opposite magnetic polarity were tangled together across the same pole at the same moment. North and south jumbled into one chaotic region, the magnetic equivalent of static hissing, where you had hoped to find a clear and steady tone. This is what the breakdown looks like, while it is actually breaking down. The old order dissolving into confusion before the new one settles into place. We had finally captured the great reversal in the very act and the long-awaited picture of our star's most fundamental rhythm, seen up close from above for the first time in history. Looked less like a clean switch being thrown and more like a vast knot coming undone all at once, every strand pulling in a different direction. It is worth pausing to feel how quietly astonishing that is. The 11-year flip had been inferred, modelled, predicted, and tracked indirectly for the better part of a century. Everyone in the field accepted it as real. No one doubted that it happened. But no one had ever properly seen it from above. Watched the polarity itself jumbled across the cap during the turn. And in a single observing campaign, the long inference became a direct image. The confident guess acquired a face at last. And the face it acquired was chaos. But here is the crucial restraint that the honesty of this story demands. Chaos captured in a photograph is not the same thing as chaos understood. Seeing the tangle does not by itself explain why it tangles in the particular way it does, or precisely how it will resolve into the new ordered field, or exactly when that resolution will complete. The image is a beginning, a first real data point where there had only ever been inference, and we will return to just how much it still leaves wide open. For now, the striking thing is simply this. The curtain was finally pulled aside on the most basic rhythm of the nearest star to Earth, and behind it, where we might have hoped to find an elegant and legible mechanism ticking smoothly along, we found instead a region in genuine turmoil. It is worth understanding, even briefly, how a spacecraft can read magnetism in light at all, because it makes the achievement feel less like magic and more like the careful detective work it is. Magnetism leaves a fingerprint in the light a glowing gas gives off. A strong magnetic field splits and subtly alters the particular colours, the precise wavelengths that the atoms emit, and it twists the way that light is oriented as it travels. By measuring those tiny splittings and twists across the whole face of the cap, point by point, an instrument can work backward and reconstruct which way the magnetic field is pointing in each patch, and how strong it is, painting a map of an invisible thing out of the visible light it disturbs. That map is called a magnetogram, and from the disk it had always been hopelessly smeared at the poles, because the light from the cap reached us through too steep and too thick a slice of the sun. Reading it cleanly required getting above the cap and looking down, which is exactly what finally happened. And what the clean reading showed, during that turbulent stretch near maximum, was a face crowded with opposing signs. A cap that should have been settling toward a single clear polarity instead caught mid-transformation, its magnetism pulling in contradictory directions across the same small region. The sunspot count was high, the star was restless, and the pole was visibly in the throes of the change. But a single map, however revolutionary, is one frame of a film that runs for years. It tells us where the field stood at one instant of one reversal, not how it got there or where it goes next. To feel the full strangeness of having waited so very long for that single glimpse. Though, you have to know that we once came tantalizingly, heartbreakingly close to seeing the poles. A machine actually flew over them, long ago, decades before Solar Orbiter was even imagined. And through a quiet cruelty of timing and technology, it could not take the picture. This was not the first time a human-made craft had visited the top of the sun. More than 30 years ago, a probe named Ulysses became the first spacecraft ever to swing up and over the sun's poles, climbing high out of the plane of the planets and passing above the very regions no telescope confined to the disk could ever properly capture. To get there, it had used the same trick of borrowed momentum, swinging out past the giant planet Jupiter to fling its orbit far up out of the plane, a long and patient detour to reach a vantage point nothing had ever held before. For a brief and genuinely extraordinary window, humanity had a machine in exactly the right place, riding high above the caps we had always missed, looking down on the poles from a height we would not reach again for a generation. And then, in one of the quiet heartbreaks of the history of space exploration, the craft could not take the photograph. Ulysses had been built to feel the sun rather than to see it. It carried a suite of instruments to taste the solar wind directly as it flowed past, to measure the magnetic field threading the space around the spacecraft, to count the charged particles streaming by its body and gauge their speed and their makeup. And it sent back priceless readings of what the polar wind was actually composed of and how fast it truly moved, confirming by direct contact that a faster, cleaner wind really did pour from the polar regions, exactly as the open field line picture had suggested. It mapped the texture and behavior of the space above the caps as no craft ever had. But it carried no camera capable of imaging the poles themselves, no instrument that could turn that region into a picture. It could stand in the darkened room and describe the shape of the walls with its hands, run its fingers carefully along every surface and report in detail what it felt, the temperature, the texture, the contours. And yet it could never reach over and switch on the light to actually see the room it was touching. So in the long years that followed, we held a precious hoard of numbers from the poles, without any face to attach them to. We knew, by direct measurement, that the fast wind came from up there. We had felt its speed and sampled its ingredients, but we had never laid eyes on the source of it, never watched the magnetic structures that produced it, never seen the caps actually doing their work. And consider, during those very same decades, what else humanity was busy seeing and triumphantly recording. We photographed galaxies so remote that the light finally reaching our instruments had left them before the Earth itself had even finished forming. We charted the faint, web-like scaffolding of matter that stretches in vast luminous filaments and immense dark voids across billions of light years, the largest structures the entire cosmos is known to contain. We captured the gentle, even afterglow of the universe's own birth, the relic warmth left over from its earliest infant moments, and read the subtle ripples in it like a map of how everything began. We assembled, image by painstaking image, a sweeping portrait of the cosmos reaching out toward the very furthest edge that light itself permits us to see. An achievement so large that the mind genuinely struggles to hold its scale. And through every single one of those triumphs of that golden age of cosmic mapping, the top of our own star, the nearest star to Earth by an almost absurd margin. The one whose light is on your face whenever you step outside, remained nothing but an unread smear at the corner of every frame. We had assembled a detailed and breathtaking atlas of the ancient, distant universe, and left a blank patch on the doorstep of our own home. We had even, by then, mapped the far side of the moon in fine and loving detail, the hemisphere that never once turns towards Earth, photographing every crater and ridge of a face no human standing on the ground had ever directly seen. We knew the hidden side of our small companion world better than we knew the top of the star that lights it. That contrast is the first genuine chill in this whole account, and it has nothing whatsoever to do with monsters or lurking dangers in the dark. It is the colder, subtler chill of realizing how badly lopsided our knowledge truly was, how far our reach had outrun our grasp of the things sitting closest to us. We stretched our instruments toward the faintest and oldest light in all of creation, and succeeded. While the brightest and nearest object in our sky kept a simple secret, merely by tilting its caps a little away from where we happened to live. The blindness was not exotic or romantic. It was almost embarrassing in its ordinariness, a matter of having stood in the wrong corner of the room for a few thousand years. There is something almost poignant in the shape of that earlier mission's journey, to climb above the plane decades ago, before the patient Venus spiral approach had been refined. The craft was flung all the way out to the largest planet and used its immense gravity as a single great lever to hurl itself up and over the sun's poles. A long and lonely detour to the outer system, simply to gain the right angle on the innermost object of all. It crossed both poles more than once across its long working life, sampling the wind above the north and the south, building a record of how the polar wind changed as the sun moved through its cycle. It learned, by direct contact, that the fast wind was real and steady, and distinct from the slower equatorial flow. It felt the magnetic field reverse its sign as the craft passed from one magnetic hemisphere to the other. All of this was genuine, hard-won knowledge, and none of it was an image. The craft returned a rich description of a place it could never show us, and then its mission ended, and the poles went back to being unseen, now merely better described. Meanwhile, the great telescopes kept pulling in the distant universe in ever finer detail. They held single patches of apparently empty sky open for days at a time, gathering the faint accumulated light until thousands of galaxies emerged from what had looked like darkness. Each one a city of stars billions of light years away. We were becoming experts in the deep past of the entire cosmos, while the present face of our own star's poles stayed a guess. And once Solar Orbiter finally climbed high enough to read the secret those caps had kept for so long, the question that had driven the entire effort did something unexpected and, in its way, unsettling. It turned itself completely inside out. Up to this point, the question driving everything had been simple, almost the question a curious child might ask while drawing the sun with a yellow crayon. What do the poles of the sun actually look like? It is a clean, natural, innocent curiosity, the kind that has always pushed explorers toward the blank spaces on maps. But the moment you truly absorb what the poles do, rather than merely what they look like, the question changes shape and gains a weight it did not have before, and this is the hinge on which the entire story turns over. The new question is no longer what the poles look like. It is what it means that the part of the sun controlling its cycles, launching its fastest wind, and staging the violent rebuilding of its magnetic field is also the part we still cannot reliably predict, the part we only just learned to see at all. Because here is the trap we have walked straight into without ever once noticing the walls closing around us. We have built an entire civilization that is sensitive to the sun's moods, far more sensitive than any society that came before us. Our power grids stretch across whole continents in long conductive lines, thousands of kilometers of metal laid out under the open sky. Our navigation, the quiet certainty of knowing exactly where we are at any moment, depends on faint timing signals from a fleet of satellites floating in the very region of space that the sun's storms disturb most violently. Our communications, our financial networks that settle by precise timestamps, our aircraft routes over the poles, our deep reliance on satellites for weather and observation and connection, all of it leans on technology that lives downstream of solar behavior and flinches whenever the sun grows agitated. And we have poured enormous effort and expense into forecasting that behavior, into trying to predict when the next stormy stretch will arrive and how fierce it will be, precisely because so much that we depend on now hangs on the answer. But the seed of that behavior, the polar field that helps set the strength and timing of the cycle to come, sat all along in the one region our forecasts were effectively blind to. We were attempting to predict the weather of an entire star while being unable to look at the place where its seasons are quietly decided. Think of the meteorologist tasked with warning a vast coastline about the severity of the approaching season, but forbidden from ever observing the one stretch of warm ocean where the great storms are actually born. They could study the records of past seasons. They could track each storm carefully once it had already formed and begun its march toward land. But they could never watch the conditions assembling at the source, never see the warmth gathering and the pressure shifting before anything took shape. And so every warning they issued would carry a hidden gap inside it, a blind region folded silently into every forecast. That is precisely the position we have occupied with respect to our own star for the whole of the technological age. This is why the comparison in the title is not idle theatrics or cheap provocation. The empty dark between the stars is genuinely awesome, terrifying in the particular way a vast and total silence is terrifying, cold and immense and utterly indifferent to whether we exist or not. It is the canvas onto which we have always painted our deepest cosmic loneliness. But the void cannot reach through your phone and scramble its signal next week. It cannot push a working satellite into an emergency shutdown to save itself, or drive a damaging surge through a continent's worth of power lines, or force airliners to reroute away from the poles. The darkness between here and the nearest star is, for all practical purposes, that touch a single day of any human life. Inert. It threatens us mainly as an idea, a beautiful and frightening backdrop, a reminder of how small and alone we are. The top and bottom of the sun are not inert in that way at all. They are active, they are decisive, and until last year they were entirely unmapped. The frightening frontier, the one that genuinely shapes the conditions under which we live, was never the cold nothing far away in the dark. It was the unread control panel of the very engine we already lean on for everything, hiding not in some distant and dramatic abyss, but in plain and blazing sight. In the only two regions of our own star, we were never once positioned to see. The dread here is not the loud dread of an invading horror crashing through the door. It is the subtler, older, more domestic dread of slowly discovering that something with enormous, daily power over your life has been operating all along in a room you did not even know was part of the house, behind a door you had simply never thought to open. And the gap was not a small or academic one. The strength of a solar cycle can vary dramatically from one cycle to the next. Some quiet and gentle, others crowded with spots and storms, and forecasters have long wanted to know, years ahead, which kind is coming, so that satellite operators and grid managers and mission planners can prepare. The most reliable early indicator anyone had found for the size of a coming cycle was, of all things, the strength of the polar field at the previous minimum, the quiet seed measured at the caps. That single fact placed the most useful predictive quantity we possess squarely in the one region our instruments could read least well. We were, in effect, trying to forecast years of a star's behavior using a number we could only estimate with a shrug, gathered from a place we had never clearly seen. Every long-range prediction of the sun's coming temper carried that uncertainty baked into its foundation, an unavoidable softness at the very base of the forecast. Improving it did not require a better theory so much as a better view, a clear, direct, repeated reading of the polar field from above, which is precisely the thing that had always been impossible from the disk. So the practical motivation behind climbing out of the plane was never mere curiosity about scenery. It was the hope of finally measuring, cleanly and repeatedly, the one quantity that might let us see the sun's seasons coming before they arrive, and to grasp just how far the reach of that hidden control panel truly extends, we have to pull back further than the sun itself, all the way out to the wall that holds the genuine void at bay. The sun does far more than warm our days and light our skies and grow our food. It builds a fortress around the entire solar system, an immense and invisible structure that most people have never once been told exists. That constant wind of charged particles streaming off the sun, the same wind whose fastest component pours from the poles, does not simply blow past the planets and dissipate harmlessly into nothing. It inflates an enormous bubble. A vast domain of space dominated by the solar wind and the sun's magnetic field. Reaching out far, far beyond the orbit of even the most distant planet, swallowing the whole family of worlds within it. Scientists call this bubble the heliosphere, and the clearest way to picture it is as a colossal tent pitched in the dark, with the sun as the single lantern blazing at its very centre, and the steady, relentless pressure of the solar wind as the force holding the great canvas taut and out against everything beyond. Outside that tent lies the true interstellar void, and it is not merely empty. It is threaded with the thin, cold gas that drifts between the stars, and far more importantly for anything alive, it is constantly raked by galactic cosmic rays. These are not gentle things. They are extremely high-energy particles, atomic fragments accelerated to nearly the speed of light and flung across the galaxy by distant cataclysms, by exploding stars and other violent events scattered through cosmic time and space. They carry enough energy to tear through living tissue and damage delicate electronics alike, to break the strands of molecules inside a cell or flip the bits inside a computer. The heliosphere, the bubble inflated by the solar wind, deflects and turns aside a very large share of these incoming particles, bending their paths and blocking their advance before they can fully reach the worlds sheltering inside. It is, in a deeply real and physical sense, the solar system's outer shield, the membrane that keeps the harshest part of interstellar space pressed away from the planets within. Now draw the threads together carefully, because this is where the whole story tightens into something genuinely uncomfortable. The solar wind that inflates and sustains this protective shield is shaped and structured by the sun's magnetic field, sculpted by it as it flows outward. And the magnetic field, at its largest and most global scale, is governed by what happens at the poles, the seed of the cycle, the source of the fast wind, the staging ground of the great reversal. So the part of the sun we could never see is not some quiet, irrelevant lid sitting harmlessly at the top and bottom. It is one of the architects of the very wall that stands between us and the genuine void. The fast wind pouring from the open field lines at the poles helps form and pressurize the bubble that holds the dark at bay. The shifting structure of the polar magnetic field helps decide how that wind flows and how the shield takes its shape and where it is strong. And here is the part that should make the hair rise. When the polar field weakens, tangles into chaos, and rebuilds itself reversed during the cycle, the structure of the shield itself shifts along with it. The bubble is not a fixed, unchanging dome standing eternally firm. It breathes. It swells and tightens in step with the solar cycle, growing more or less robust as the sun's activity rises and falls over the years. During the sun's more active, more strongly magnetized stretches, the shield tends to hold back more of the incoming cosmic radiation, clamping down harder against the dark. During the quieter, weaker stretches, more of that radiation from outside leaks through and reaches into the system, and the timing and intensity of those breathing cycles trace back, in part, to the very polar field we had never been able to properly observe until last year. We are not entirely guessing about where this great tent ends either, because two of our oldest spacecraft have actually reached its edge. After flying outward for decades, the twin probes launched in the 1970s eventually crossed the far boundary of the bubble, the place where the outward pressure of the solar wind finally gives way to the pressure of interstellar space beyond. As they crossed that frontier, their instruments recorded a sharp change. The count of particles coming from the sun dropped away, and the count of galactic cosmic rays from outside climbed, a measurable handover from the sun's domain to the galaxies. That boundary is the literal edge of the sun's reach, the outer skin of the protective bubble, and crossing it was the first time anything human-made had passed from inside our star's influence into the true interstellar medium beyond. It confirmed, in the most direct way imaginable, that the shield is real and that it has an edge, that there genuinely is an inside and an outside, a sheltered region and an exposed one. And the strength of that shelter is not constant. As the sun's magnetic activity rises and falls across its cycle, the amount of galactic cosmic radiation that reaches the inner system rises and falls in the opposite rhythm. More cosmic rays sneaking through when the sun is quiet and its field is weak, fewer when the sun is active and its field is strong. The dark between the stars, in other words, presses harder on us in some years than in others, and how hard it presses is set by the changing magnetism of the sun, which traces back to the poles. This is the moment the title's strange claim lands with its full and proper weight. The void does not reach us, and the reason it does not reach us runs, in significant part, straight through the two regions of our own star that no human eye had ever clearly seen until 2025. The thing standing between us and the dark was, all along, being assembled in the place we had been forced by simple geometry to ignore. We had always pictured the void as the threat and the sun as the comfort, and that picture is not wrong, exactly, but it was incomplete in a way that should genuinely unsettle anyone who follows it through. The comfort and the protection were being built, in real and significant measure, by the very part of the sun we could not examine, the part whose deepest workings we still cannot fully predict even now that we have at last seen its turbulent face. The wall against the void has a foundation, and that foundation is precisely the region whose behavior remains, to this day, the great unsolved mystery of our own star. Bring all of this down from the grand scale of bubbles and galaxies and cosmic rays to the scale of an ordinary life, to lights and screens and the solid ground beneath your feet, and the stakes stop feeling abstract almost immediately. When the sun's activity climbs towards its maximum, it does not merely paint prettier curtains of aurora across the far northern and southern skies, though it does that too. It produces flares, sudden and intense bursts of radiation that race outward at the speed of light and arrive at Earth in minutes. And it hurls enormous eruptions of charged material out into space. Vast clouds of solar plasma flung away from the star and sent barreling across the system. When one of those great eruptions happens to be aimed at Earth, it eventually slams into our planet's own magnetic field, the smaller shield that wraps our world specifically, and can set off what is called a geomagnetic storm. A powerful storm of that kind can do real and varied damage. It can disrupt radio communications across whole regions, blacking out the high-frequency channels that aircraft and ships and emergency services rely upon. It can degrade or scramble the precise navigation signals that ships, aircraft, and the phone in your pocket all quietly depend on for their sense of location. It can force satellites into protective shutdown modes to survive the onslaught of charged particles, and can shorten their working lives or knock them out entirely. It can expose astronauts in orbit to elevated and genuinely dangerous doses of radiation, a serious concern as we plan longer journeys beyond the protection of Earth's field. And in the most severe cases on record, it can drive powerful electrical surges through the long conductive lines of a power grid, the kind of induced currents that can overheat and damage the heavy transformers at the heart of the system and, in the gravest scenarios, threaten the stability of electricity supply across a wide and populated area. We have wired nearly every essential system of modern life to infrastructure that the sun can reach out and rattle from across 93 million miles of empty space. And the intensity of these stormy stretches rises and falls with the solar cycle, the very cycle whose eventual strength is helped into being years in advance at the poles. So the practical chain of cause and effect runs like this. Link by sobering link. The polar magnetic field, the region we could not see, helps set the tone and strength of the coming cycle of activity. The strength of that cycle shapes how many violent eruptions the sun is likely to produce over the following years, and how powerful they may be. The number and force of those eruptions help determine how often and how severely our grids and our satellites and our signals are put under strain. Which means our ability to anticipate the next difficult decade of space weather has, all along, depended on reading a part of the sun that our forecasts simply could not properly observe. It is rather like a city that grew and electrified itself for generations, laying down an ever denser nervous system of cables and circuits through every street and building, while never once locating the master breaker panel that governs whether the whole system runs smoothly or surges and fails. The city thrived. The lights stayed on, mostly. But the panel was always there, out of sight, quietly deciding, and only now have we found the door to the room it sits in. This is not a hypothetical worry conjured for effect. History records real events of this kind, carefully studied and well documented. In the 19th century, before the electrical age had truly begun, a tremendous solar storm lit up auroras far closer to the equator than anyone had ever seen, and sent currents surging through the young telegraph networks of the day, in some cases shocking operators and setting equipment sparking, even letting some lines run briefly on the storm's own induced current after the batteries were disconnected. In more recent decades, severe storms have knocked out satellites, forced aircraft on polar routes to divert to avoid radio blackouts and radiation exposure, and, in at least one well-known case, induced currents strong enough to collapse a regional power grid and leave millions without electricity for hours in the depth of winter. These were not the end of the world. People endured them, repaired the damage, and carried on. But each one was a small demonstration of the same chain, the sun reaching across empty space to disturb the machinery we have woven through our lives. And each one would be more consequential today, now that so much more of what we do depends on satellites and grids and precise timing than ever before. The deeper point is not that any single storm spells catastrophe, but that their frequency and their severity ride on the cycle, and the cycle's strength is seeded where we could not look. The city built its nervous system street by street, generation by generation, growing ever more dependent on the steady flow of current through it, and the master panel that governs whether that flow stays smooth or surges dangerously sat in a room nobody had ever entered, deciding quietly in the dark. We are only now standing at the door of that room with a light. There is a strong temptation, hearing all of this laid out, to slide toward alarm, and it is important to resist that honestly and firmly. Nothing here says a catastrophe is imminent or even likely soon. There is no prediction of doom folded into these facts, no claim that the next reversal will harm Earth directly, no suggestion that the sun is somehow turning against the life it has always sustained. The reversal is a perfectly natural rhythm the sun has performed countless times across billions of years, and life on Earth has always carried on straight through it, cycle after cycle after cycle, entirely untroubled by the flip itself. The unsettling part is something narrower, quieter, and far truer than any apocalyptic tale spun for attention. It is simply that the engine our entire civilization now leans upon has a control region we had never once learned to look at directly, and that our forecasts of its moods carried that blindness folded inside them the whole time. Like a missing page in an instruction manual we never knew was incomplete. We built the wiring first, across the whole world, and found the control room only afterward. And even now, with the first clear images of that room finally in hand, the view through the newly opened door raises at least as many questions as it answers. Perhaps more. It would be dishonest and a quiet betrayal of the very thing that makes the story worth telling, to pretend that one extraordinary set of images solved the sun's deepest puzzles. The pictures of that disordered South Pole are a genuine first in the history of our species, a real and lasting achievement. But they are a single viewpoint, captured during one particular phase of a long cycle, near the turbulent peak of activity, from a vantage point that is still only modestly above the plane. They show us the field in disarray, but they do not yet reveal the underlying rule that the disarray obeys. Seeing a knot is not the same as understanding how it came to be tied, or how it will eventually come loose, or what knot will replace it. Solar physics is still living alongside several real and stubborn mysteries that the poles touch upon, but do not, on their own, resolve. And intellectual honesty requires laying them out plainly, rather than letting the genuine drama of a single image quietly paper over the gaps. We still do not fully understand how the dynamo works in its deepest detail, how exactly the churning, spinning plasma generates and organizes the sprawling field it produces, and why it keeps such regular time across cycles that otherwise vary in strength. We do not fully understand how the magnetic flux migrates toward the poles over the course of years to seed the next cycle. The precise way the raw material of the coming reversal gathers itself up at the caps, drifting poleward from the spotted middle latitudes. We cannot reliably predict, far enough in advance to be genuinely useful, how strong any given solar maximum will turn out to be, which is, of course, exactly the prediction our increasingly sun-sensitive technology would most dearly love to have in hand years ahead of time. Forecasts improve, but the deep predictability we want still escapes us. And hovering over all of these specific puzzles is an even older and more famous one, a problem the poles may help to illuminate, but have certainly not yet cracked. The Sun's outer atmosphere, its corona, the faint pearly crown that leaps into view around the black disk of the Moon during a total eclipse, is staggeringly, almost absurdly hotter than the visible layer beneath it. This should not be possible according to all ordinary intuition about how heat behaves. Heat is supposed to flow from the hotter thing to the cooler thing, from the fire outward into the cooler air around it. Yet here, at the Sun, the thin outer atmosphere blazes at temperatures hundreds of times higher than the surface it sits directly above, as though the air a short distance above a campfire was somehow vastly hotter than the flames at its base. Some process is dumping tremendous energy into that outer atmosphere, heating it far beyond the surface below. And no one has a complete, settled, universally accepted explanation for how it happens. The poles, with their open magnetic field lines and their fast outflowing wind, are among the most promising places researchers hope to find decisive clues to that century-old riddle. There is a sharp difference in science between a photograph and a film, between catching a thing once and watching it unfold. And that difference is exactly what the poles still demand. A single magnetogram of the cap, taken at one moment near maximum, is a freeze frame of a process that takes the better part of a decade to complete. It is as if we had been handed one still photograph from the middle of a long and complicated dance and asked to explain the whole choreography from that alone. We can see the dancers are in motion, that limbs are mid-gesture, that something is clearly happening, but we cannot see what step came before or what step comes next. Cannot tell whether the tangle we are looking at is the chaos building toward the flip or the chaos beginning to resolve after it. Only a sustained watch, frame after frame across years from a steady high vantage point, can turn that single photograph into the film we actually need. And there is a related puzzle the still image cannot settle. The question of how the magnetic material even reaches the poles to seed the next cycle in the first place. The Sun appears to have slow, vast flows running just beneath its surface, currents of plasma that drift from the equator toward the poles and sink back down again deep inside, carrying magnetic flux poleward over years like a conveyor belt feeding the caps. The exact speed and depth and reliability of that great conveyor remain poorly pinned down, and yet it may be central to how each cycle hands off to the next. The poles are where that conveyor delivers its cargo, and watching the delivery happen, repeatedly, is one of the things the coming years of observation are meant to capture. So the first clear images of the polar caps are emphatically not the closing chapter of a long investigation. They are the opening of a fresh notebook. The first page filled in where every previous page had been left blank. They give us, for the very first time, real, direct data where before we had only inference and clever modelling. A measured face where before we had only an educated guess sketched hopefully from the side. That is a profound step forward. And it should not be undersold in the rush to either reassure or to frighten. But a single high-angle glimpse of one pole, taken during one chaotic phase of the cycle, from one viewpoint that is still climbing toward its best angles, is the honest beginning of a careful inquiry, not its triumphant verdict. The foreshortening that plagued all the old views is reduced, but it is not yet erased. The view is of one cap caught in one moment, not yet a steady, prolonged, patient study of both poles across an entire cycle from a truly commanding height. Treating these first, remarkable pictures as a final and complete answer would betray the very discipline that makes the genuine story so compelling. The discipline of holding wonder and caution in the same steady hand at once, refusing to let either one crowd out the other. The mystery of the poles has not been solved by these images. It has, for the first time in the entire history of our species, been properly photographed. And what makes the years that lie just ahead genuinely thrilling, rather than merely unsettling, is that the photographing has only just begun, and the next and far more ambitious stages are already designed, funded in part, and quietly on their way upward. There is a particular kind of unease that comes not from any immediate danger, but from sheer scale. From suddenly grasping how small and how late in the story we truly are. And the poles deliver that unease cleanly and without mercy. Consider the depth of time involved here, and try to hold it honestly in your mind. The 11-year cycle, the slow winding and the violent reversal, the tearing down of the field, and its painstaking reassembly the other way around, has been running for billions of years. It was turning in the dark long before there were any eyes anywhere in existence to watch it. It was turning before the first fish swam, before the first cell divided, before the earth had even cooled and gathered itself into a solid world at all. It is a rhythm far older than every fossil ever pulled from the rock, older than every ocean that has ever filled a basin and later drained away, older than the very first breath ever drawn by anything that breathes. The sun has flipped its entire magnetic field countless times in total darkness and total silence, with no audience of any kind, performing the same vast and intricate act over and over while the planets formed and reformed, while continents drifted and collided, while life crawled up out of the warm water and, slowly, across unimaginable stretches of time, built languages and cities and instruments. And then, only in the very last fraction of a heartbeat of that immense and indifferent span, one small and fragile species finally managed to point a machine at the right angle to look directly at the act as it happened. And what that long-delayed, hard-won glance revealed was not a serene, comprehensible mechanism quietly keeping perfect time like a great clock. It was a region caught in turmoil, a dense tangle of opposed polarities, a control room that, on its very first honest inspection, looks chaotic and remains only partly predictable even to the experts who have studied its effects for their entire careers. That is the true and honest shape of the dread at the centre of this story, and it is worth naming with care so that it is not mistaken for something cheaper and louder. It is not the dread of an imminent disaster bearing down on us. It is the dread of belatedness, the strange vertigo of realizing that we have built a wired, deeply interconnected, profoundly sun-dependent civilization right on top of a process whose control region we managed to examine directly for the very first time only last year, and which we still cannot fully read or forecast. We laid the cables across the continents and launched the great fleets of satellites, and tied our navigation and our power and our communication and our timekeeping to the ancient rhythms of a star. And only afterward, only once everything depended on it, did we finally manage to look directly at the place where those rhythms are set. And when we looked, we found something we do not yet fully understand. There is a deep humility hidden in that sequence, and a quiet fear, and the two are tangled together as tightly as the opposing polarities at the pole itself. The fear is most certainly not that the sun is somehow hostile to us. It plainly is not, and never has been. It has nurtured and sustained every living thing that has ever existed on this planet. And the great reversal has never once interrupted that long nurture, never once flickered the light of life. The fear is something more precise and more human than that. It is the recognition of dependence without comprehension, the unsettling sense of standing inside a vast and humming machine room whose master controls you have only just managed to locate and cannot yet operate, cannot yet read with confidence, cannot yet reliably forecast. For almost the whole of human history, we did not feel this particular unease at all, because we did not know nearly enough to feel it. We saw the sun rise and set with perfect dependability, and we assumed a comforting, eternal steadiness behind it, a simple lamp that merely burned and would go on burning. Now we know that the lamp has a switchboard, that the switchboard sits precisely at the 2 points we could never see, and that the switchboard behaves in ways that surprised even the people who have devoted their lives to the sun when they finally got their first clear look at it. The comforting steadiness was perfectly real on the short timescale of a single human life. And it remains real enough to plan around. But it was always, all along, riding on top of a deeper, stranger, and only now visible machinery. It sharpens the unease further to count how briefly we have truly been watching at all. People have noticed the sun's spots for a few centuries, and have kept careful, continuous records of the cycle for only a couple of 100 years. We have studied the sun from space, with instruments that can see what the eye cannot, for mere decades. Set that against a rhythm billions of years old, and our entire history of close attention amounts to a handful of cycles, a few dozen turns of a wheel that has spun untold hundreds of millions of times. We are not seasoned observers of our star. We are newcomers who arrived a moment ago, glanced at a few beats of an ancient pulse, and are now trying to predict its future from the thinnest sliver of its past. And the part of it we most needed to watch, the poles, we did not see clearly even once until last year. So everything we believe we understand about the long behavior of the sun rests on an extraordinarily short record, gathered mostly from the wrong angle, with the most important region left blank. This is not a reason for despair, but it is a reason for humility. And humility is precisely what the polar images quietly enforce. They remind us that the confidence we feel about the sun, the sense that it is a solved and steady thing, comes partly from how little of its life we have actually witnessed. A process can look perfectly regular when you have only seen a few of its repetitions, and reveal its irregularities only over the long haul we have not yet lived through as observers. The chaotic cap is a warning against mistaking our brief familiarity for real understanding, and the proper response to that recognition is neither panic nor denial, but the one thing science does better than anything else, which is to look harder, to climb higher, and to turn that first fleeting glimpse into a long, patient, unblinking gaze. Because the most remarkable part of this entire account is not, in the end, what we have already managed to see. It is what we are. For the very first time in the long history of life on Earth. About to be able to watch, what changes everything from here is that the spacecraft which finally looked down at the pole is nowhere near finished with its climb. Solar Orbiter is on what its own scientists have nicknamed, only half in jest, a stairway to heaven. And the phrase turns out to be far more literal than poetic. Every time the craft swings past Venus and threads the gravitational slingshot just right, it borrows a little more of that planet's vast orbital momentum and tilts its own path a few degrees further up and out of the flat plane of the planets, lifting its vantage point higher and higher above the sun's poles with each carefully planned encounter. The first clear images, the ones that revealed the tangle at the South Pole, came from a relatively modest tilt, a first cautious step up the long staircase. Future encounters are designed and scheduled to raise that angle further still, each planned pass by Venus nudging the inclination of the orbit steeper, carrying the craft to ever higher perches, from which the caps will appear progressively less squashed, less foreshortened, more honestly and fully revealed. Each single step up the stairway means a cleaner, fuller, less distorted look down at the regions we ignored for the whole of history, until what began as a first uncertain glimpse becomes something far closer to a true and steady overhead portrait of the top and bottom of the star. And Solar Orbiter is not the end of the ambition, only its opening act. The first climber to reach the lower steps. Other missions are being designed and planned with the explicit, deliberate goal of climbing even higher above the plane than Solar Orbiter ever will, of reaching vantage points steep enough to hover above the poles for long, sustained stretches rather than merely catching them in passing during the high point of an orbit. The aim of these future efforts is to keep a steady, continuous eye on the polar field through the slow building of the magnetic strain and the eventual violent flip. To watch the great reversal happen from directly above as it unfolds, rather than reconstructing it afterward from scattered clues gathered at an angle from the side. The plans look ahead to the years around the next expected reversal, with the hope of catching the entire turn of the field in real images from a commanding height. The climb is also designed to keep paying off for years, not merely to peak once. With each further Venus encounter, the tilt of the orbit is meant to grow, lifting the best viewing angle higher across the coming years until the craft looks down on the caps from a steepness no mission has ever managed. And because the orbit repeats, the spacecraft returns to a high vantage over the poles again and again, building not a single portrait, but a series of them spread across the changing seasons of the sun. The raw material of that long-needed film. Already there are firm plans for the craft to revisit the poles from progressively better angles in the years immediately ahead, each return a little higher than the last. Beyond it, the missions now being designed aim higher still, toward orbits steep enough to hold the poles in view for extended stretches, rather than glimpsing them at the top of each loop, and timed deliberately to be watching when the field next turns itself over. If those ambitions are realized, we would gain something no generation has ever possessed: a continuous record of a pole through a complete reversal. The seed gathering, the order breaking down into the chaos we have now seen only as a single frame, and the new order assembling itself reversed. All of it captured in sequence from above. The flip would stop being an inference stitched together after the fact from clues at the edge of the disk and become, for the first time, a thing directly witnessed. A film of the sun changing its mind. Sit with what that genuinely means for a moment, because it is without any precedent in the history of life. The reversal has been occurring for billions of years, an intricate act performed endlessly in the dark with absolutely no one watching, no eye to register it. And we are about to become the first generation in the entire history of anything that has ever lived on Earth that can look directly down into the control room while the switch is actually being thrown. We will be able to see the old field dissolve into chaos and the new, reversed field assemble itself out of the wreckage in real images, from above, as it happens in real time. The blind spot that lasted for all of recorded history is not being erased in a single dramatic stroke. It is being opened slowly and deliberately, step by patient step, angle by improving angle, as our machines climb laboriously up and out of the flat record we have always been confined to. Each pass by Venus is another stair beneath our feet. Each new mission designed for the poles is another whole flight of stairs above that. And with every increase in height, the smeared and unreadable region at the edge of all the old images resolves a little further into a real, studied, comprehensible place. The last great blank on the map of our own star, slowly and methodically being filled in by hand. There is something almost redemptive in the shape of that arc, after so many long centuries of standing helplessly in the wrong part of the room. We could not see the poles for the whole of history because of where we happened to be born, on a small planet riding a flat disk around a star whose caps were forever tilted just out of reach of our gaze. And rather than accept that limit as permanent and final, we found a way to climb out of the disk itself, to steal a little momentum from a neighbouring world, pass after patient pass, and slowly lift our gaze up above the very plane that had always confined us. No previous generation could have done this, not for lack of will, but for lack of altitude. And no future generation will have to do it for the first time again. As that gaze continues to rise and sharpen over the coming years, something quietly profound happens to the very first image we began this whole story with, the familiar one, the one you have carried in your mind, unexamined, your entire life. Return now to that opening picture, the one we started with, the familiar orange disk with its scattered dark sunspots and its blazing rim, the sun exactly as it has always been shown to us in every book and every screen. For your entire life, that image has felt complete. It felt like a true portrait of the whole star, a full and honest likeness with nothing of importance left out. But now, carrying everything you have come to understand across this account, look at that image again and feel how the meaning of it shifts and slides beneath you. That was never a portrait of the whole sun. It was a profile. It was the front of a face, captured beautifully and in extraordinary fine detail, while the top and the bottom of the head stayed quietly turned away, out of the frame, and the parts that were turned away were precisely where the switchboard sat, where the real decisions were being made. Every gorgeous, scientifically rich, hard-won image of the sun ever made before that first high-angle campaign was, in this exact and inescapable sense, an incomplete document. Accurate about the broad, bright middle, yes, and genuinely so, but silent about the two regions that may well matter most to how the star actually behaves over the years and decades. We were not wrong about what we saw in all those images. The spots were real. The eruptions were real. The churning, granular surface was real and beautifully captured. We were simply never shown the rest of it, and we mistook the visible half for the whole because we had no choice in the matter and nothing whatsoever to compare it against. With no view of the poles ever available, there was no way to feel their absence, no obvious gap in the picture to point at and wonder about. The profile looked like a complete portrait, precisely because we had never once seen a real portrait to know the difference, never had the fuller image that would have revealed how much was missing. Think of what that does to the entire archive of solar images humanity has gathered, the vast library of pictures and films, built up over a century of devoted watching. None of them becomes wrong, exactly, but every one of them quietly acquires a caption it never had before, an unspoken footnote that says, and the part that runs all of this was just out of frame, above and below, unseen. The famous photographs of great eruptions, the time-lapses of spots marching across the disk, the eclipse images with the corona flaring around the dark moon, all of them were honest records of the performance on the lit stage, taken by an audience that did not know the wings existed. And there is a generational dimension to this that is easy to miss. Every person who has ever lived until now grew up with that profile as their mental image of the sun. The bright circle, the spotted middle, the rays a child draws. But the children being born now may grow up in a world where the full sphere is simply known, where the poles are mapped and filmed and ordinary, where the idea that we once could not see the top of our own star sounds as quaint and almost unbelievable as the idea that we once did not know what the far side of the moon looked like. The blind spot that defined the whole of human history with the sun is closing inside a single lifetime. And to those who come after, the strangeness will not be the chaotic cap. It will be that we went so long without ever seeing it, that we built so much on a star we had only ever viewed from the waist. This is the strange, quiet vertigo of the polar images, and it is a genuinely different sensation from any of the earlier turns this story has taken. It is not the dread of the empty void. It is not the unease of dependence without understanding. It is not even the cold chill of belatedness. It is the specific disorientation of having the deeply familiar retroactively rewritten in front of you, of watching something you were certain you knew quietly become something else. The new pictures from above do not simply add one more image to the long and treasured collection. They reach backward through time and change the meaning of every single image that came before them. The sun was always a sphere, of course. It always had a top and a bottom. It always carried those chaotic, decisive caps, doing their crucial work out of our sight, seeding the cycles, launching the fast wind, dismantling and rebuilding the global field, helping to shape and pressurize the great shield around us all. None of that machinery is new. It has been running the whole time. What is new is only our sudden ability to see it at last. And that single addition quietly reorganizes everything we thought we already firmly knew. We kept the camera level with the star's waist for the whole of history, not out of any carelessness or lack of curiosity, but simply because the waist was the only place we were ever allowed to aim from, and across all those centuries, we quietly let the part we could see stand in, unquestioned. For the whole, we could not. The result is a single fact that should genuinely give anyone pause when they first truly grasp it. The most familiar object in the entire sky, the one that a small child can draw without any instruction at all, a simple circle with rays, the one whose warmth and light define the basic rhythm of every single life that has ever existed on this planet, turns out to have been, until just last year, among the least completely seen large objects anywhere in our entire cosmic neighborhood. We had mapped the permanently hidden face of the moon, the side that never turns toward us, in fine and careful and complete detail long before. We knew the far side of our small companion world far better than we knew the top of the very star that lights it and gives it its glow. It is a humbling thing to sit with, that the object we drew first as children and trusted most as adults was the one we had seen least completely of all. And that one realization, more than any single dramatic image of tangled polarity, reframes the entire emotional weight of the claim we began this story with, and gathers all the scattered threads toward the point they have been building toward all along. So here is where every thread we have carefully followed finally draws together, and the strange comparison in the title at last stops sounding like exaggeration and begins instead to sound like a careful, measured, almost humble statement of plain fact. The void between the stars is empty. That emptiness is vast and cold and entirely worthy of our deepest awe. And there is a real and genuine terror in honestly contemplating it. The terror of pure scale, of total silence, of an indifference so complete it cannot even notice us. But the void is, in every single way that touches the actual conditions of our daily lives, inert. The dark, stretching from here to the nearest star, holds nothing that will alter your sky tomorrow. Nothing that decides whether the coming decade brings gentle solar weather or fierce and damaging storms. Nothing that presses against the shield protecting the worlds we live on, or breathes in time with the rhythm of our star. The void threatens us chiefly as an idea, a magnificent and humbling backdrop against which our small, warm, crowded planet glows like a single lit window in an endless night. The top and bottom of the sun threaten us, if threaten is even the right word for it, in a completely different way. The way a working mechanism threatens, the way the engine you depend on but do not understand threatens. They hold the seed of the cycle that governs the sun's violence in the years ahead. They hold the source region of the fastest wind in the entire system. They hold the staging ground of the great reversal that periodically flips the whole global field on its head. And they hold a real share of the architecture of the very shield that keeps the genuine void itself held safely at arm's length. The breathing bubble that rises and falls in its power to turn aside the radiation pouring in endlessly from the wider galaxy. Terror. When you finally follow it all the way down to its root, turns out not to be about distance or darkness at all. It is about consequence meeting uncertainty. It is about something mattering enormously while remaining, at the same time, beyond our understanding. The void is distant and dark, but it is, in its own way, certain and silent and predictable, a known and stable quantity that mostly leaves us entirely alone to live our lives. The poles are close. They are blindingly bright. They are anything but silent, churning constantly through their tangled work, and yet, until just last year, they were profoundly uncertain to us, unread, a mechanism of immense and direct importance to our lives that we had simply never once managed to examine. That precise combination is the true source of the unease running through this whole story. Something powerful, something we depend on utterly, at every level of our wired and connected existence, and something we could not see, and still, even now, cannot fully predict. It is not the loud dread of a monster crouched in the dark and waiting to spring. It is the older, subtler, more genuinely human dread of slowly realizing just how much was being decided all along in a room you did not even know you were standing right next to, by a quiet process you had no idea was there, a process upon which your lights and your signals and the very shield over your entire world quietly and constantly depend. We had built our whole house up against that door and furnished every other room and never once turned the handle. Not out of fear, but out of simple inability. Because the handle was on a side of the wall we could not reach. The poles are not evil. They are not hostile. They have faithfully nurtured everything that has ever drawn breath. The unease comes precisely and entirely because they are so very important and were so completely unseen, hidden from us not by any design or malice or cosmic cruelty, but by the plain, stubborn, accidental geometry of where we happen to be born, on a flat disk circling a star whose caps were always tilted just a little out of view. We mistook the front of the face for the whole of it, and lived our entire history beneath a switchboard we never even thought to look for. And only now, climbing slowly and at last up out of the plane that confined us, have we begun to truly see the part of our own star that may matter most of all. It is worth being precise about why those two ingredients together produce dread, when neither alone would. Plenty of things matter enormously to our lives and frighten no one, because we understand them well enough to feel safe. The changing of the seasons, the turning of day into night, the steady pull of gravity. And plenty of things are deeply uncertain, yet trouble no one, because they have no real bearing on us. The exact arrangement of pebbles on a beach we will never visit, the weather on a planet circling a distant star. Dread lives precisely in the overlap, in the narrow place where something both matters greatly and remains beyond our grasp. The poles sit squarely in that overlap. They are not a distant curiosity we can afford to leave unsolved, because they touch the shield over our world and the temper of the star we depend on. And they are not a settled, understood mechanism we can take for granted, because we have seen them clearly only once, and what we saw was turmoil. That is the whole anatomy of the unease, laid bare. High stakes and low certainty meeting in the same place, at the top and bottom of the one object whose steadiness we had always quietly assumed. And the particular flavour of the fear is not dramatic but intimate, the flavour of the room next door. It is the difference between fearing a storm far out at sea and realising there is a door in your own home you have walked past every day without ever opening, behind which something has been quietly running the house. The storm at sea is grander and more obviously frightening, but the unopened door is closer, and the not knowing is sharper, precisely because it was always within reach, and you simply never looked. That is where the sun's poles have lived in our awareness, behind a door an arm's length away, unopened for the whole of history. And that long journey brings us, finally, all the way back down to something as small and immediate and ordinary as the warmth resting on the back of your hand. So the next time the sunlight falls warm across the back of your hand, hold this in your mind for just a moment longer than you usually would. That warmth is reaching you from a star you have looked at, in one form or another, your entire life. A star so utterly familiar that it barely registers as a wonder anymore, just the ordinary bright thing in the daytime sky. And yet, there are exactly two places on that star that no human eye saw clearly until last year. Two regions, at the very top and the very bottom, turned away from us all this time by nothing more dramatic than the simple tilt of our own existence, by the plain accident of being born on a flat disk whose level never once lined up with the caps. And those two long unseen regions may quietly decide more about the sky above you, about the storms and the calm, about the strength of the shield over your world and the radiation it turns aside, than all the immense darkness stretching from here to the nearest star ever could. We mapped the faint edge of the observable universe before we mapped the lid of our own lantern. We learned the distant faces of galaxies whose light is older than the Earth itself before we learned the near face our own sun had always kept turned quietly away. We even came to know the hidden side of the moon, every crater of it, before we knew the top of the very star that lights it. And now, for the first time in the long and patient history of anything that has ever lived beneath this sun, a small and persistent machine is climbing higher above the plane we have always been confined to, lifting its gaze degree by careful degree, steadying itself for a sustained and unblinking look at the part of the sun that helps build the wall against the void, the part that tears itself apart and rebuilds itself reversed with every slow turn of the cycle. The void will keep its silence, as it always has and always will. It has nothing whatsoever to say to us, and no way to reach across that immense and indifferent dark to touch a single hour of a single life. But the poles are not silent, and they never were. They are awake, and they are working, churning ceaselessly through their tangled reversal as they have for billions upon billions of unwatched years. And they are only now, at long last, beginning to come into clear and honest view. Somewhere above and below that bright, ordinary, endlessly familiar disk, two caps of knotted plasma are quietly seeding the next decade of our sky, dismantling one ancient magnetic order and patiently assembling another in its place, and turning slowly all the while toward a small camera that has finally, after all of human history, found the right place to stand and look. Think, for a moment, about how strange and intimate that relationship really is. The light on your hand left the surface of the sun about 8 minutes ago and crossed the empty space between us to arrive exactly here, on your skin, now. It is the most direct, daily, physical contact any of us has with another celestial body. This constant, gentle touch of starlight, so ordinary that we never think of it as touch at all. And the engine that produced that light, that has produced it faithfully every single day of your life and every day of every life before yours, runs on machinery we have only just begun to see. The warmth is utterly reliable. The lamp has never once failed in all of human experience. And yet the controls of that lamp sat in shadow until last year, at the 2 points we were never positioned to look. There is a particular feeling that comes from holding both of those truths at once. The absolute dependability of the light and the near total mystery of its deepest workings. It is not fear, exactly, and it is not comfort, exactly. It is something closer to awe with a cold edge to it. The awe of realizing that the most familiar thing in your world has been quietly keeping a secret in plain sight for as long as anything has lived to feel its warmth. We tend to think of discovery as reaching outward, pushing the frontier ever further into the dark, toward fainter and stranger and more distant things. But this discovery ran the other way. It reached back toward the most familiar object of all and found that we had never truly seen it whole. The frontier was not in the depths of the void after all. It was overhead and underfoot, at the top and bottom of the one star we thought we had long since taken the full measure of. Step outside into it sometime and let it rest on your face the way you have 10,000 times before, and let the ordinary miracle of it register just once. The light is the same light. The star is the same star. Only our knowledge of it has changed, and even that only barely. Only at the very edges. Only at the 2 caps we have just begun to glimpse. And so the slow climb continues, pass after pass, degree after degree. A small machine spiraling higher above the plane that held us level for so long, carrying our gaze at last toward the parts of the sun that were always there and always working and never once seen. The most frightening thing in our corner of space was never the emptiness between the stars. The emptiness. For all its vast and beautiful cold immensity, simply waits and asks nothing of us. and decides nothing about our days. The genuinely frightening thing, the truly unsettling thing once you have seen it clearly, was always closer and brighter and far more important to us than the dark ever was. It was the unread top and bottom of the one star we were so completely certain we already knew. Still half in shadow even now, still being mapped a little more clearly with every patient climb above the plane, still turning in its slow and ancient rhythm, still doing, in full view at last, what it has always done in the dark. And still, quietly and without any ceremony at all, deciding the weather of a small world that only just learned to look up at the right angle.